There is something lurking at the center of nearly every galaxy in the universe. Something that devours stars, bends the very fabric of reality, and creates regions where time itself grinds to a halt. And the most unsettling part? It is not actually an object. We call them black holes, but that name is deeply misleading. A black hole is not a thing floating in space the way a planet or a star is a thing. It is a wound in the geometry of the universe, a place where the normal rules of space and time have collapsed so completely that our physics breaks down entirely. Everything we think we know about cause and effect, about up and down, about past and future, stops working at the edge of a black hole. And that is exactly why they matter. Because by studying the places where the rules break down, we learn something profound about the rules themselves. In this video, we are going to take a journey through the life and death of a black hole, from the violent stellar explosions that create them, to the bizarre quantum tricks that ultimately destroy them. We will explore a phenomenon called Hawking radiation, a process so strange it forces us to ask whether the matter inside a black hole is even real in a meaningful sense. We will look at how spinning black holes tear spacetime into a whirlpool, and how we might one day extract enormous amounts of energy from that whirlpool. And at the end, we will look at the mathematical mirror image of a black hole, an object that spits matter out instead of swallowing it, and ask the most mind-bending question of all: could our entire universe be one of those objects? Let's start at the beginning. Let's start with a star. Every star in the sky is a war. On one side, gravity, the crushing, relentless pull of the star's own mass, trying to collapse it into a single point. On the other side, nuclear fusion. Deep in the star's core, hydrogen atoms are being slammed together with such force that they fuse into helium, and that process releases an enormous amount of energy that pushes back outward against gravity. This balance is called hydrostatic equilibrium. As long as the star has hydrogen to burn, the two forces stay roughly equal, and the star remains stable. But hydrogen is not infinite. Eventually, it starts to run low. For smaller stars like our Sun, this is where the story ends. The star swells into a red giant, sheds its outer layers, and the core becomes a dense, slowly cooling remnant called a white dwarf. Dramatic, but relatively quiet. For massive stars, the giants 8 or more times the mass of the Sun, the story is far more violent. When hydrogen starts to run out, the core contracts and heats up until it can fuse helium into carbon, then carbon into neon, neon into oxygen, oxygen into silicon. Each fusion stage burns faster than the last, and each one produces a new element. The star is building up layers, like an onion, with heavier elements at the center. And then it reaches iron. Iron is where the fusion chain terminates. The reason is thermodynamic. Every previous fusion reaction released energy because the resulting nucleus had less internal energy than the components going into it. That leftover energy is what powers the outward push. But iron is different. Iron is at the very bottom of the nuclear binding energy curve. Fusing it doesn't release energy, it consumes it. Iron just sits in the core, piling up, contributing nothing to the fight against gravity. And then, in a fraction of a second, the scales tip. The iron core collapses. What happens next is one of the most violent events in the observable universe. The core rebounds off itself in a shockwave that blasts through the entire star, ejecting its outer layers at a significant fraction of the speed of light. We call this a supernova. For a brief period, the explosion can outshine an entire galaxy of hundreds of billions of stars. But the shockwave leaves something behind. If the original star was massive enough, the core that remains is not a neutron star, a dense ball of neutrons roughly 25 kilometers across. Instead, the core keeps collapsing, and collapsing, and collapsing. There is nothing left to stop it. Our physics reaches a point it cannot describe, and what remains is a singularity, a point of theoretically infinite density, wrapped in a sphere of no return. We call that sphere the event horizon. And that is where things get truly strange. When you look at a photograph of a black hole, the kind that made headlines in 2019 when the Event Horizon Telescope first imaged one, you are not seeing the black hole itself. You are seeing its shadow. The dark circle at the center of that glowing ring of superheated matter is the event horizon, the boundary beyond which nothing, not particles, not information, not even light, can ever return. It is not a physical surface. There is no wall there, no membrane you can touch. It is a geometric property of spacetime, a threshold defined entirely by the fact that gravity, past this point, has become so overwhelming that the escape velocity exceeds the speed of light. Think about what escape velocity means. When a rocket launches from Earth, it needs to reach about 11 kilometers per second to break free from our planet's gravity. If you were standing on a neutron star, you'd need to move at roughly half the speed of light to escape. At the event horizon of a black hole, you would need to exceed the speed of light itself, and nothing in the universe can do that. So anything that crosses the event horizon is gone. From the perspective of the universe outside, it has ceased to exist in any practical sense. But here is where things get philosophically disturbing. Time itself behaves differently near the event horizon. Einstein showed us that gravity and time are inseparable. Mass warps spacetime, and that warping affects the rate at which time passes. The stronger the gravitational field, the slower time runs. This is not science fiction. It is measurable. GPS satellites have to account for it because they experience weaker gravity than we do on Earth's surface, so their clocks run slightly fast. We adjust for this every single day. Near a black hole, this effect becomes extreme. If you watched an astronaut falling toward the event horizon, you would see them slow down. As they approached the boundary, their movements would become more and more sluggish. Their signal would redshift into radio waves, then into silence. From your perspective, they would never actually cross the horizon. They would appear to freeze there, dimming into invisibility. Time, for them, would appear to stop. From the astronaut's perspective, though, they would cross the event horizon without necessarily noticing anything unusual in their immediate surroundings. The passage would feel normal. What they would eventually notice, if they survive long enough, is that the entire future of the external universe would appear to play out in an instant above them. The time dilation is so severe that from inside the event horizon, the outside universe ages faster, in a sense. And beyond the horizon lies the singularity, a point where our equations spit out infinities and stop making sense. We do not have a theory that can describe what happens there. It is one of the great unsolved problems of modern physics. But something remarkable happens before you even reach the singularity. Something that changes everything we thought we knew about what black holes can and cannot do. For most of the 20th century, it was assumed that black holes were permanent. Once formed, they would exist until the end of time, growing larger as they consumed matter, but never shrinking, never dying. The event horizon was a one-way door, and everything that fell through was lost forever. In 1974, Stephen Hawking turned that assumption on its head. His paper, titled Black Hole Explosions, proposed something radical. Black holes slowly evaporate. They lose mass over time by emitting radiation, now called Hawking radiation, and eventually, over timescales vastly larger than the current age of the universe, they vanish entirely. This seems impossible. If nothing can escape a black hole, how can it radiate energy? The answer requires us to understand something deeply strange about the nature of empty space. What is nothing? Take a volume of space, a cubic meter of absolute vacuum.
No atoms, no dust,
no light passing through. Is that nothing? The answer, according to quantum field theory, is no. Completely empty space is not nothing. It is a seething, churning field of quantum activity that only looks calm at the macroscopic scale. To understand why, we need to introduce the concept of quantum fields. In the modern picture of physics, every particle is not really a particle in the traditional sense. It is a localized vibration, an excitation, of an underlying field that permeates all of space and time. There is an electron field, and electrons are ripples in that field. There is a photon field, and photons are ripples in that field. Every type of particle corresponds to a field, and these fields fill the entire universe. Now here is the key insight. These fields are not completely still, even in regions we call vacuum. Because of a fundamental principle of quantum mechanics, Heisenberg's uncertainty principle, the value of any quantum field at any given point can never be perfectly nailed down to zero. There is always some residual quantum uncertainty, and the consequence of this is that quantum fields constantly fluctuate, even in empty space. This fluctuation does something extraordinary. It causes particle-antiparticle pairs to momentarily pop into existence, a particle and its antimatter counterpart, created from nothing, existing for an immeasurably short time before annihilating each other and vanishing back into nothing. These are called virtual particles. They are not metaphors or theoretical constructs. There is direct experimental evidence for their existence. This evidence is called the Casimir effect. In the 1940s, physicist Hendrik Casimir predicted that if you placed two uncharged metal plates very close together in a vacuum, they would experience a tiny attractive force pushing them together. Why? Because the space between the plates restricts which virtual particle pairs can form. Only pairs whose wavelength fits between the plates can appear in that region. Outside the plates, all wavelengths can form. The result is a slightly higher virtual particle density outside the plates than inside, creating a pressure difference. The plates are pushed together by nothing, by the quantum noise of empty space. The experiment has been done many times. It works. Virtual particles are real. Now, what does any of this have to do with black holes? Hawking realized something profound about what the event horizon does to this quantum vacuum. Normally, virtual particle pairs form and annihilate almost instantaneously. They are borrowing energy from the uncertainty principle, and the universe demands it back quickly. But at the boundary of a black hole, something different can happen. If a virtual pair forms just outside the event horizon, there is a chance, a quantum mechanical probability, that one member of the pair falls inside the horizon before the pair can annihilate. The other member, finding its partner gone, can no longer recombine. It becomes a real particle, carrying real energy away from the black hole. But energy must be conserved. If a real particle with real energy is escaping the black hole, something must pay that energy bill. And the something that pays is the black hole itself. The mass of the black hole decreases slightly with each Hawking radiation event. Over vast timescales, this process drains the black hole entirely. There is a further implication that is even more disturbing. The temperature of Hawking radiation is inversely proportional to the mass of the black hole. A stellar mass black hole emits radiation at a temperature so cold, billionths of a degree above absolute zero, that it is completely undetectable against the cosmic microwave background. But as the black hole shrinks, its temperature rises. As it approaches its final moments, the process accelerates dramatically, culminating in a burst of energy release. A black hole does not just evaporate, it explodes. Now, this has not been directly observed for real black holes. They are all far too large and the radiation far too cold to detect. But in 2016, researchers at the Technion Institute in Israel built an analog of a black hole using a quantum fluid, a configuration where phonons, sound quanta, cannot escape past a certain boundary, mimicking the way photons cannot escape past an event horizon. They ran the experiment 97,000 times over 124 days and detected radiation matching Hawking's predictions with remarkable precision. The math works. And if the math works for sound, it almost certainly works for light as well. The existence of Hawking radiation is strange enough on its own, but it carries an implication that is perhaps the most philosophically unsettling idea in modern physics, an idea that calls into question the nature of physical reality itself. Here is the issue. Hawking radiation does not come from inside the black hole. It does not come from the singularity or even from the event horizon itself. It is generated in a region of space outside the black hole, a region potentially billions of kilometers away from the horizon, purely as a consequence of the way the black hole curves spacetime. The radiation is not escaping from inside. It is being created outside. This means something strange about the relationship between the black hole and its radiation. Normally, we think of causes as producing effects. A fire produces heat. A moving object produces a wake. The black hole, with all its mass, all its gravitational power, produces a curvature of spacetime around it, and that curvature produces Hawking radiation. The mass causes the curvature causes the radiation. That is the order we intuitively expect. But Einstein's equations for general relativity do not specify that this ordering is mandatory. The equations relate mass and spacetime curvature, but they do not say which one is the cause and which one is the effect. The relationship is proportional, not directional. You can run the equations forward or backward. This is where Hawking radiation becomes philosophically explosive. If the curvature of spacetime radiates energy, and if that radiation reduces the curvature, and if the reduction in curvature reduces the mass, then the sequence of causality is inverted. The curvature is not the shadow cast by the mass. The mass is the shadow cast by the curvature. Let that sit for a moment. What we experience as solid matter, as mass, as substance, might not be fundamental. It might be a projection, a consequence of the geometry of spacetime. In this view, space is the primary reality, and matter is what happens when space is severely bent. Think of it this way. Hold your hand up and project a light at it. The shadow on the wall is real in the sense that you can observe it and describe it. But it is not fundamental. It is a consequence of your hand's geometry interacting with the light. If you move your hand, the shadow changes. The shadow is downstream from the hand. The projection hypothesis about matter is saying, what if we are the shadow? What if the curvature of spacetime is the hand, and what we experience as mass and substance is merely the observable consequence of that curvature? What if matter, like the shadow, is real in a derived sense, but not fundamental? This is, to be clear, not an established fact. It is an implication of the mathematics, a possibility that the equations permit but do not definitively prove. But it is a genuine scientific hypothesis, not merely philosophical speculation. And here is what makes it genuinely disturbing. You cannot tell the difference from the inside. If you were a shadow and you did not know it, how would you know? From inside your reference frame, you would have experiences, thoughts, a sense of continuity. Reality would feel solid and real. You would have no way of distinguishing between being a primary entity and being a projection of one. Black holes, by breaking the normal rules of spacetime, offer us a lens through which we can ask questions about those rules that we could not otherwise formulate. And some of the answers that come back are uncomfortable. Not all black holes are the same. The simplest black holes, what physicists call Schwarzschild black holes, are those that neither spin nor carry electric charge. They are perfectly spherical, utterly static, and described by a single number, their mass. But in the real universe, virtually every black hole spins. When a massive star collapses, it conserves angular momentum, the same principle that makes ice skaters spin faster when they pull in their arms. As the star's core contracts from thousands of kilometers across to a few kilometers, any initial spin at it gets amplified enormously. Real black holes rotate at close to the maximum rate physically possible, and that rotation does something remarkable to the spacetime around them. Einstein showed us that mass warps spacetime. What he also showed, though it took longer for the implications to be appreciated, is that a rotating mass does something more. It drags spacetime along with it as it rotates. Imagine spinning a bowling ball in a pool of honey. The honey near the ball would begin to rotate too, not because it was pushed, but because the rotation of the ball drags the fluid around it. This is called frame dragging. For ordinary objects like the Earth, frame dragging is real but incredibly subtle. We can only detect it with the most sensitive instruments in existence, like the gravity probe B satellite. But around a rapidly spinning black hole, frame dragging is not subtle. It is violent. Around a spinning black hole, there exists a region outside the event horizon called the ergosphere. It gets its name from the Greek word for work, ergon, because this is a region where work can, in principle, be extracted from the black hole. Within the ergosphere, the dragging of spacetime is so extreme that it is physically impossible to remain stationary. Even if you were directing all your thrust against the rotation, you would still be dragged around the black hole because the space you are sitting in is itself rotating. You cannot stand still in the ergosphere any more than you can stand still on a moving walkway. What is even more extraordinary is the speed at which this spacetime rotation occurs. Near the event horizon of a rapidly spinning black hole, the ergosphere reaches speeds where spacetime itself is moving faster than the speed of light. But this does not violate Einstein's rules, because those rules only prohibit objects from moving faster than light through spacetime, not spacetime itself from moving. This creates an extraordinary situation. Deep in the ergosphere, matter is being dragged around at an appreciable fraction of the speed of light, purely by the geometry of spacetime. No force is being applied. It is not being pushed. It is simply moving because the stage on which it sits is moving. And if you can extract that motion, you can extract enormous energy. Energy not from matter falling into the black hole, but from the rotational kinetic energy of spacetime itself. This is the Penrose process. The physicist Roger Penrose proposed a mechanism by which an object entering the ergosphere could, under the right conditions, split into two parts. One part falling into the event horizon on a trajectory that reduces the black hole's angular momentum, and the other part being ejected outward carrying more energy than the original object brought in. The excess energy is real, and it comes from the rotational energy of the black hole. Theoretical calculations suggest that up to around 21% of the black hole's total mass energy could be extracted this way, and because of Einstein's E equals mc squared, that represents a staggering amount of energy. A single kilogram of mass energy extracted from a black hole via the Penrose process would release the equivalent of about 15 kilotons of TNT. This is not quite science fiction. It is a real mechanism consistent with general relativity. Whether humanity could ever engineer such an extraction is another question, but the universe does not seem to have prohibited it in principle. Here is a question that sounds like it belongs in a science fiction novel. If black holes are defined by the property that nothing can escape from inside them, do their mathematical opposites exist? Objects from which nothing can fall in, where matter and energy can only flow outward? The answer, at least mathematically, is yes, and they are called white holes. To understand white holes, we need to think about how physicists describe the geometry of spacetime around a black hole. One of the most useful tools for this is something called a Penrose diagram, a way of mapping all of spacetime, including its infinite past and infinite future, onto a finite picture. The rules are elegant. In a Penrose diagram, light always travels at 45-degree angles. Anything that must travel slower than light, which is everything with mass, can only move at angles steeper than 45 degrees. Draw the Penrose diagram for a standard, non-rotating black hole, and you get 4 regions. Region 1 is the normal universe, the observable cosmos, stretching from infinite past to infinite future. Region 2 is the black hole interior, separated from the universe by the event horizon. You can see in the diagram why it is a one-way door. Any path that crosses the horizon, traveling at 45 degrees or steeper, inevitably hits the singularity. There is no path that leads back out. But the mathematics of general relativity are symmetric in a certain deep sense. When you solve Einstein's equations for a black hole, you do not get just regions 1 and 2. The complete mathematical solution contains 4 regions. And region 3, sitting on the other side of the singularity, is a region with the singularity in its past rather than its future. In this region, light can leave but not enter. Matter can escape but not fall in. It is the time reversal of a black hole, a white hole. Now, before you get too excited, no white hole has ever been observed, and there are strong reasons to think that the white holes predicted by the simple mathematical solution may not survive in the messy real universe. Black holes in reality form from collapsing stars, and this formation process breaks the mathematical symmetry that creates the white hole in the theory. So white holes may be mathematical artifacts, features of the idealized equations that do not correspond to anything in the physical universe. But there is a more speculative and intriguing possibility that has gained serious attention in recent years. When Hawking radiation eventually evaporates a black hole down to the Planck mass, around 22 micrograms, our standard equations of quantum mechanics and general relativity stop being reliable. We enter a regime that requires a full theory of quantum gravity, which we do not yet have. One candidate theory, called loop quantum gravity, suggests that something remarkable happens at this scale. Instead of the black hole collapsing into a true singularity, quantum effects prevent the collapse. The black hole bounces, and when it bounces outward, it becomes a white hole, slowly radiating its stored information back into the universe. This is deeply significant because it offers a potential resolution to something called the information paradox. If matter falling into a black hole is truly destroyed, if the information encoded in that matter is permanently lost, then this violates a fundamental principle of quantum mechanics, which says that information can never be truly destroyed, only scrambled. Hawking radiation alone doesn't solve this problem, because standard Hawking radiation is thermal. It carries energy but not information. The loop quantum gravity white hole scenario suggests that all the information that fell into the black hole over its lifetime is eventually, slowly, over timescales almost incomprehensibly vast, radiated back out through the white hole phase. This is speculative, but it is grounded in real mathematics and addresses a real problem. And there is one more implication, the most staggering of all. In general relativity, our universe has a singularity in its past. 14 billion years ago, at the moment of the Big Bang, all the matter and energy in the observable universe was compressed into an infinitely small, infinitely hot point, a singularity, and then expanded outward. In the language of a Penrose diagram, our universe looks, from the outside, like a region with a singularity in its past from which matter is flowing outward. That is exactly the definition of a white hole. Our universe, in the most literal mathematical sense, is consistent with being the interior of a white hole. Not a black hole, we are not being crushed inward. A white hole, we are inside a region of spacetime from which things can only expand outward, seeded by a singularity in the past. If loop quantum gravity's prediction is correct, if black holes eventually bounce and become white holes, then the obvious question is, what was the singularity of our Big Bang? Was there a black hole on the other side? Was our universe born from the death of a black hole in some other universe? This idea is not entirely without support. Loop quantum cosmology, the application of loop quantum gravity to the universe as a whole, suggests that the Big Bang was not a true beginning but a big bounce. Before the Big Bang, there was a contracting universe that reached a maximum density defined by quantum gravity effects, and then bounced outward into what we experience as the expanding universe we live in. Under this scenario, black holes, white holes, and the universe itself are all part of one continuous cycle. A black hole forms in one universe. It evaporates. At the final moment, it bounces into a white hole. The white hole is the seed of a new universe. That universe expands. Stars form. Some die as supernovas. Some leave behind black holes. And the cycle continues, an eternal recursion of creation and destruction, with each generation of universe seeding the next. This is not established science. The experiments needed to test these ideas are beyond anything we can currently build. But it is remarkable that the mathematics is consistent with it, that nothing in our known physics prohibits this scenario. Black holes began as a mathematical curiosity, a solution to Einstein's equations that seemed too extreme to be real. Within a few decades, they went from theoretical artifacts to observed phenomena. We have now directly imaged them, detected gravitational waves from their mergers, and measured the supermassive black hole at the center of our own galaxy. What started as the most extreme, most destructive objects imaginable has become something more. They are mirrors, objects that reflect back at us the deepest questions about the nature of space, time, matter, and existence itself. Every time we look into them, we find the universe is stranger than we imagined. And we have barely begun to look.